All right, I'll get started now. Okay, cool. So this meeting, I'm going to be talking about one of my favorite codes and kind of a code that combines a lot of ideas that I'm very interested in terms of mathematics, and these are Reed-Solomon codes. And hopefully throughout this meeting, you'll see why some people call it the greatest code of them all. But yeah, first I'm going to introduce you guys to the code and a little bit of background and history of the code. So the general idea of the code is pretty simple, right? So how many roots does a degree D polynomial have, right? So like how many zeros can it have at most, right? So we have like a line, whatever. If you have like a straight line, right? What's the maximum number of roots it can have? 1, right? And if we have a quadratic, degree 2, 2, right? So in general, the fundamental theory of algebra exactly says that a polynomial of degree at most d of degree d has at most d roots. And then so the idea is that we're going to somehow encode messages as evaluations of polynomials. And if we don't have too many roots of our polynomial, right? So not too many zeros when we do evaluations, then our code words aren't going to have too many zeros and they'll have a good distance. That's kind of the rough idea that we're going to be working with. And then so quick notation is, you've probably seen this before. It's like f sub q, or you've probably seen f sub p, or like the integers mod q, where q is a prime power. So if q is just a normal prime number, then this is kind of what you're used to, just modular arithmetic. But it turns out you can do this for like integer, like something mod p squared or p cubed or something. And I'm not going to go into details of that. It doesn't really matter for this. But the point is, we're gonna be working over like finite fields. So if you're comfortable with modular arithmetic, then for all intents and purposes, you can just think of it as a normal prime. So like mod 7 or mod 11, something like that. And then you'll see this notation where I'll add like this x to it. And so these are polynomials where the coefficients live in this field. And so, for example, if the field is something like integers mod 3, then 2x squared is a polynomial in this, f sub 3x, right? Because it's a polynomial, something like x squared is a polynomial, and the coefficient 2 lives in that field. So we're all happy. And so here is what a Reed-Solomon code is, right? And I'm going to unpack this definition. So we have some values, q, n, and k, whatever. So I'm going to pick n values out of our field. And these are going to be distinct values. And these are going to be the evaluation points, right? So alphas throughout are going to be evaluation points. And so then the alphabet of our messages are going to be the integer, like the finite field mod q. And so the way we're going to generate our code is we're going to look at all possible polynomials f, evaluate them at all of the evaluation points, and put it into like a vector or like a list or whatever. And that's going to be our code word. And the important thing is these polynomials all have degree less than or equal to k minus 1. And that's the idea. So I'll walk through an example of this. And so here's our code, right? And then how do we encode something? Well, if we have a message, m0 whatever, right? So all of these are integers mod q. So we can define, like, we can use these numbers as coefficients of our polynomial. So like the 0th number, it could correspond to a constant term. The first m sub 1 corresponds to x to the 1. M sub 2 corresponds to x squared, right? And you get this polynomial. And so we can take that, and then when we encode it, we're just going to evaluate this message, we're gonna get this polynomial, and we're gonna evaluate it all the evaluation points. And I'll try to make this a little bit more concrete. But I'll make it more concrete in a second. But the important thing about why we like these codes is, if you remember back to Hassan's meeting, these are linear codes. You can add and subtract polynomials like you do with vectors. And really the idea is that polynomials of degree less than or equal to k minus 1 are a k-dimensional vector space. And vector spaces have a bunch of nice properties. That's why a lot of mathematics kind of reduces things to linear algebra. And so there are generator matrices. So we could instead take a message and multiply it by this generator matrix, and you would get the code. It doesn't really matter. I'm not going to use the generator matrix again ever, but oh, that term right there should go. But yeah, there's a generator matrix. It's a linear code. It's not going to be super important that it's linear for the rest of this meeting, but it's a fact that is quite essential to the properties. But let's go over an example. So we're going to be working over, in this example, integers mod 7, and then we're going to have 4 evaluation points, and we're going to encode a message of length 3, right? So let's have our evaluation points be 1, 2, 4, and 6, right? So those are the integers. And then remember, that's our encoding function. So if we want to encode this message 135, right? So just looking at this formula, what is the corresponding polynomial going to be? Yep, exactly. 1 plus 3x plus 5x squared. And that's going to live in this, right? All the coefficients are integers mod 7, and it's a polynomial. So it lives inside this set of all polynomials, right? Does everyone see why this f sub m of x is this polynomial for that message? And then how do we encode it? Well, we're going to evaluate it at all of these numbers, right? So we're going to compute f sub m of 1, f sub m of 2, f sub m of 4, f sub m of 6. And I'm not going to do the math. No one wants to. Just if you do the multiplication and the addition, it works out to this. But that's the idea. So we've encoded this message into this code word just by constructing this polynomial and evaluating it. Right? So everyone on board with how these codes work, how we can encode. Yeah.
And so, like, one of the advantages that we have more, that the amount of evaluation points that we use equal to the degree of how many people encoded. But we have 4 evaluation points, so we have up to the degree of 4 polynomials.
Yeah, and that's gonna come up later. We need as many evaluation points. We need at least as many evaluation points as we do the length of the message, because later when we do decoding, we're going to kind of use the fact that like how many points do you need to define a straight line? 2, right? So like a degree 1 polynomial needs 2 points. And then how many for like a degree 1 polynomial needs 2 points. How many points do you need to define a quadratic? You need 3, etc. So we can kind of use that idea for decoding, but that's why that restriction's there. Good question. Yeah. Okay. But so that kind of abstract definition kind of more concrete now? All right, cool. But now we know how to encode things. How do you decode these polynomials? And so Reed and Solomon, when they first published this code, I think it was in 1960 when they were at Bell Labs. I'm not exactly sure. I forget the year. But we had the code, and we would, in theory, like to recover the message. It's kind of the whole point of coding theory. So how did they do it? So the degree of the polynomial is k minus 1, right? And like I said, to uniquely define a k-1 degree polynomial, you need k points, right? A line is degree 1 and you need 2 points, a quadratic is degree 2, you need 3 points, etc., etc. So we're going to choose any k of the evaluations out of the n that are there. And then we're going to interpolate these points, and what that means is that there's a way, given, like, if I give you some number of points and I say, here are 3 points, give me the quadratic that goes through these 3 points. There's a process to do that. It's called interpolation, which I'll go into in a minute. You can interpolate those points and you can find this polynomial f, right? Because you know that you evaluated f to get these evaluation points, right? That's how it was encoded. And we want to recover that polynomial, right? Because if we want to recover that polynomial, read out the coefficient and get the message. And so you can do this for all n choose k choices of evaluations, and you'll get some coefficients, right? You see like this coefficient for the zero, for like the zero term, this coefficient for the x term, this coefficient for the x squared term, blah, blah, blah. There might be some differences depending on errors and stuff. And then so you could just see which coefficients appear the most often and pick the one that appears most often to get the right coefficients. And I hope you can kind of see that's not super efficient, right? If n is quite large and k is small, then n choose k is a massive number, right? N choose k is going to be of degree n minus k. So there's gonna be a lot of choices. It gets really slow really quickly. And so we kind of want to get around this. But I'm going to first kind of go into what interpolation is, because I think it's like one of those fundamental like algorithms you'll see in mathematics, and it's not too hard of an idea. And the core idea is this, right? If 2 polynomials of degree less than or equal to k-1 agree on k points, then they must be the same polynomial, right? Because we know you need that many points to uniquely define the polynomial. And then so if we have some function f, okay, some polynomial f of degree less than or equal to k-1, then we're going to have alpha 1 through alpha k distinct points. Then this polynomial, which I will explain later, we're going to kind of build up to it, is the Lagrange interpolating polynomial. Right? So Lagrange was this great mathematician in algebra and a bunch of other fields. And so that's what the polynomial was kind of named after. And I'm going to claim that this polynomial L is equal to whatever f was. And then, so then the takeaway from this is that if I just give you what alpha 1 and what f of alpha 1 should be, then you can plug it into this formula and you'll get the polynomial that generated those evaluations. Right? And then, but then why does this work? Okay, so there's a definition of L that we're going to kind of build up to it slowly. Right? So let's just look at this product for a second. And I kind of want to consider 2 possibilities. Whether or not x is equal to this alpha I. So like this product, we're going from j equals 1 to k of alpha I minus alpha j, and we're not doing alpha I minus alpha I, so no division by 0. So everything's kind of clear. So we're kind of, so this is going to have k-1 terms. And then we have x minus alpha j. And then so if x is equal to alpha I, then what is this product going to be equal to? It's just going to be 1, right? Because the numerator and the denominator is always going to be the same. And then what if x is equal to one of the other alpha, like say like let's say it's like equal to, I don't know, alpha sub L. That's not equal to alpha sub I on this list. What is it going to be equal to? What is this product going to be equal? Why is it going to be 0? Yeah, right? Exactly. So that alpha L is not gonna be equal to alpha I, that's the other case. And so that means it's gonna appear somewhere in this, it's gonna be one of the alpha sub j that we're gonna enumerate through. And then so we're gonna eventually get alpha sub L minus alpha sub L in the numerator. So we're gonna get a 0. And then a product times 0. So you get a product of a bunch of things times 0. And that's just gonna be 0, right? So yeah, it's gonna be 0. So this is either gonna be 1 or 0, depending on which alpha we choose. All right, so now if I multiply this product by f of alpha I, so then what is this gonna be equal to if x is equal to alpha I? It's just gonna be f of alpha I, right? Nothing's changed, and then similarly, it's still going to be 0. Right? And then so, this, so now this is just the original polynomial we are kind of going towards. And then we can see that this polynomial is going to be equal to f of alpha I if x is equal to alpha I for some I. Right? So everyone can see that? Because one of these terms will be equal to f of alpha I if x equals alpha I, and all the other terms of the summation are going to be 0. So you're going to get f of alpha I plus a bunch of zeros, just f of alpha I. Right? And then so what's the key takeaway? Is that L and F agree on k points. They're equal to each other on all of the alpha I, right? And what did I say about polynomials that of degree k minus 1? That agree on k points? They must be the same. So this is so these polynomials are equal on all points, right? And then so if you have the evaluations, and so in Reed-Solomon codes, right, everyone knows what the evaluation points were, and then you get this code word, and that's the outputs. So you have all the inputs, you have all the outputs. You can do this interpolation and recover what f sub m is supposed to be, right? And so that's interpolation. So that's kind of the original Reed-Solomon decoding algorithm. So you do all possible interpolations, get the polynomial, and read out the coefficients. So I guess like before I move on, does anyone have any questions? All right, cool. So I guess a little bit about the history of these codes. So in 1960, Reed and Solomon published the original paper. And then in 1968, 69, two other mathematicians, Berlekamp and Massey, they kind of improve on this, on the decoding algorithm. But I'm not gonna get into this algorithm. But then in 1986, Berlekamp and another guy, Welch, designed an even faster decoding algorithm, and that's the one I want to go over in the later part of the meeting. It's kind of the one that everyone uses to do Reed-Solomon decoding. And then if you kind of go into like what coding theory is like nowadays, there are these things called list decoding methods, which are about which are like some more complicated techniques, and list decoding is covered in some courses in U of I. I think there are a couple like randomness, like topics courses that'll cover this stuff. So it's using like techniques of randomized algorithms to do decoding. So it's kind of like the most modern Reed-Solomon decoding algorithms. But the one I'm going to talk about today is going to be this one from 1986, since I think it's a relatively simple algorithm. It's quite fast. But why do we care about Reed-Solomon codes? So probably the most widely used application for Reed-Solomon codes is QR codes, right? If you think about it, QR codes appear outside in the elements. And then so they are kind of subject to the weather and all sorts of errors, right? Something might get scratched out, like, you know, something might fly into it and stain it or whatever. And your phone still needs to be able to scan it. Or you can maybe even modify some of the bits and create art, kind of representing what you want this to connect to. So this is a QR code that if you scan, it goes to the website for the Go programming language. And the Go programming language has like a little gopher as the mascot, which you might recognize in this QR code. And then CDs were probably the first mass-produced item to use Reed-Solomon codes, and they kind of cover, and they're kind of combined with a lot of burst errors techniques that were covered in the last meeting. So you take QR codes and burst error techniques, you get what's used in CDs for fixing scratches and stuff. And they're probably like something you guys might have seen around with a lot of like the stable diffusion stuff that's been popping up is people have really abused this idea, and you can get this is a scannable QR code despite it not looking like a QR code at all. And so people have been using what's called stable diffusion and AI to really like get an image as close to one image as possible while still being a readable QR code. And then one thing you'll see if you try to actually design one of these yourself is that if you look at the QR spec, is that like QR codes have like different levels of like robustness. And then so they go from like, I think the levels of robustness are 7%, 15%, 25%, and 30%, which is like the percentage of points in the QR code that can be lost before the QR code is completely unreadable. So if you use the most robust QR code out there, you can lose about 30% of the data to you lose about 30% of the data and still recover the original URL. Yeah, so Reed-Solomon codes are used in a bunch of stuff. All right, so any questions? Yeah.
So if I actually scan that short on the last page, will it work?
Yeah, it goes to like some,
Yeah,
it goes to like some website that allows you to design these things, I think. There you go for it.
It didn't work for me.
It didn't?
It worked for me.
It worked for me. Wait, that's crazy.
And then like too far off axis or something.
I'll upload the
Maybe
slides.
the phone is just bad.
I'll upload the slides, you can try. Yeah,
It's basic.
yeah, I've seen a lot of these like online. They're kind of cool. I'm gonna throw it away. All right. So next I want to talk about what's called the singleton bound. And then so the singleton bound is if you have a code over an alphabet of size q, so we were working over finite fields of size q, and they're encoding messages of length k into codes of length n with distance d, then this is kind of like a relation that must hold when you are looking at codes. And the reason why we care about this relation is like if you plot rate versus distance, so recall the rate is like the how much like the code, like the length of the message divided by the length of the code word, right? So a rate of 1 means the code word is the length of the original message, and so nothing really changed in terms of length. And then as rate gets lower and lower and lower, your code word is getting much longer relative to the original message length. And then so the important thing is, if you remember from like the Hamming codes meeting, there's the Hamming bound. And what the Hamming bound tells you is that kind of these areas above the line are impossible. So you can never achieve like a rate and distance trade-off above this line. And the singleton bound improves this for q greater than 2. In certain cases, the singleton bound is a much stronger lower bound. So you can't get trade-offs in this direction. So it improves the Hamming bound. And so it's a much stronger impossibility result. And like the whole rate versus distance trade-off is kind of the main game. Is like the main game of coding theories. Like you want to be able to increase this maximum distance while keeping the rate low. You don't want to have a bunch of overhead, a high rate, but you still want to be able to correct a lot of errors. So you want a high distance. So this trade-off is kind of important. And then so the proof isn't too bad, right? So if we take some code word right? In C so it's gonna be of length n. I'm gonna keep the first n minus d plus 1 bits of the code word, and I'm gonna call that phi of C. So I need a name for it. We're gonna call that phi of C, and then the idea is we're gonna discard the rest of this. And then, so, I'm gonna let C tilde be the set of all phi of C's. So I'm gonna apply phi to every single code word. I'm gonna get the C tilde. It's gonna be a set of words of length n minus d plus 1. And I'm gonna claim that C and C tilde have the same cardinality. They have the same number of elements. And if not, then you would have that phi of C is equal to phi of C prime for some C not equal to C prime, right? Two words must have gotten mapped to the same phi. But this is a contradiction. The distance of C and C prime would have to be less than or equal to d minus 1, right? That's how many letters we discarded. We discarded C minus 1. We discarded d minus 1 letters. And so if we know the first, if phi of C is equal to phi of C prime, then the first n minus d plus 1 elements are the same. And so the maximum difference had to have come from the last d minus 1 characters. So their distance is less than or equal to d minus 1. But we said the code had distance d, which is the minimum distance. And so we found two code words with distance strictly less than the minimum, which is impossible. And so that's a contradiction. And then what this tells us is that C is the size of C is equal to the size of C tilde, which is less than or equal to Q to the n minus d plus 1. Because it's a subset of the set of all words of that length, of length n minus d plus 1. And so if it's a subset, its size has to be less or equal to that, right? And then so that means K, which by definition is log base Q of the code, of the size of the code, is less than or equal to n minus d plus 1. And so we get this proof of the bound via simple contradiction. Make sense? Right. And then so there's a theorem out there that says that Reed-Solomon codes meet this bound. So the distance of Reed-Solomon codes with these evaluation points over this field of size Q, messages of length K, blow it up to codes of length N. The distance is N minus K plus 1. And then the intuition for this, I'm not going to go into a proof of this because it's kind of boring. But the intuition for this is that polynomials have at most K minus 1 zeros, right? Because these are all the polynomials are of degree K minus 1. And so they have at most K minus 1 zeros. And then so that kind of gives you, so that means at most, in their code word of length N, at most K minus 1 elements are zeros. But that's just an intuition. That's not a full proof. But since distance is N minus K minus 1, or plus 1, my bad, we can correct at most N minus K over 2 pairs. Maybe like with a floor in there. And then so, a nice little definition is that any linear codes that exactly meet this bound, such as Reed-Solomon codes, because remember they're linear. So they're what are called maximum distance separable codes. And there's a big open conjecture out there stated in the 50s that the statement is super important. But the point is that if you have linear MDS codes satisfying certain properties, then they must if you have a linear MDS code, then you must have n is less than or equal to Q plus 1. And the reason I put this at is still a massively open problem in coding theory. I like resolving this would be a huge step forward in coding theory, but it's been open since the 50s for a reason. Certain special cases have been proven, but Yeah, so even though Reed-Solomon codes are relatively well understood, there's still a lot of open problems surrounding them. Yeah, any questions? If not, I'll go into decoding. Alright. So I promised a more efficient decoding algorithm. And we're gonna cover the Berlekamp-Welch decoding algorithm. Right? So if we're given some code word out of our Reed-Solomon code, and it has at most, like, say, E errors, so E as this upper bound. We want to find the polynomial f with degree, let's say, let's equal to k minus 1, like that. So degree of f is not equal to k minus 1, remember? And f of alpha sub I is not equal to c sub I at most E times, right? Because that's what an error is. An error is when f of alpha I is not equal to c of I. And then so here's the idea, right? So let E of x be this magic error locating polynomial, which I'm going to define as the product of all alpha x minus alpha I, which is where the errors are located. So these are all I, where c sub I is not equal to f of alpha I. I'm going to do x minus alpha I. And the reason it's called the error locator polynomial, is that we have this relation that c times e of alpha, c of I times e of alpha I is equal to f of alpha I times e of alpha I. For all alpha I, for all possible I. And then so if c of I is equal to alpha I, then this is obvious, right? But what if c of I is not equal to f of alpha I? What happens? Huh? You get 0 on both sides, right? Yeah. So c of I is not equal to f of alpha I. Then E evaluated at alpha I is equal to 0, right? Because it's one of the alpha I, and then you get alpha I minus alpha I, take a product, you get 0 times whatever, you get 0. And then so you get 0 and 0 on both sides. And then so the idea is we're going to find this polynomial E and a polynomial Q such that f of x is equal to, such that Q is equal to f times E. Right, so that if we find E and we find Q, we just do division and we find F. Simple enough? Let's give you like the 2 steps. Find E and Q and then divide. That's it. So all of the work is just going to be finding these polynomials. And then so there's a quick lemma that these polynomials actually have to exist. If they didn't exist, that'd be kind of bad. So suppose that there is some degree less than or equal to k minus 1 polynomial, f, such that the distance between the message, that is a typo. That should be the encoding event, right? So let's say this is our original message polynomial, right? So suppose there was some original message polynomial where the distance between the encoding of that polynomial and C, our original code word, the errors weren't too big. There was less than or equal to E errors. Then these polynomials E and Q exist. So E is going to be a monic polynomial, so its leading coefficient is going to be 1. And Q is going to be a degree less than or equal to E plus K minus 1. And that's just so because remember we did Q times we did Q is equal to E times F. If you just take the products of those two, then that's what the degree turns out to be. And we wanted that E is equal to Q for all alpha I, and that's what we said before. If you remember, right? Because that's just what Q is. Q is that thing right there. So you want E is equal to Q. Right, so why do these polynomials exist? I'm gonna write them out for you. E is just this polynomial. And everything I've written down here exists, right? So the polynomial must exist. And E exists and F exists by assumption. So their product must exist. And since I've written it down, the polynomials exist. So it's not a complicated proof, but does that make sense? The polynomials exist because I've written them down explicitly. We know all these properties hold by what we saw in the previous slide. Yeah. Oh, C was like the code word that we had originally. Like we wanted to code this code. So I'm basically saying, I should add that to the statement. Like we have the code word and we want to find the original message associated that mapped to that code word. Yeah, but C might have errors. So it's like the encoding of M versus like the code word with errors. So it's like, yeah, so like CI might or might not be an error. But then the encoding of M by assumption it has no errors because we haven't transmitted. We've only encoded, we haven't transmitted it yet.
And we don't know.
No, we're trying to find that, yeah. I'm just trying to argue that these polynomials exist. Because once we know they exist, we can solve for them and divide. But yeah, these polynomials exist. Is kind of like the key takeaway. And then so now I want to find these polynomials. So how do we do that? So what are polynomials, right? They're just these summations of these coefficients. Some powers. And since we know that C of I times E of alpha I is equal to Q of alpha I, well then their difference must be 0. Right? And then so this just gives us a bunch of linear equations. And then so we have n linear equations, one for each I, right? Each code word or each letter. And then that previous lemma tells us that if there aren't too many errors, then some solution must exist. And then so we can simply solve this system of equations. And if a solution exists, we're done. We found our E and Q. And if some solution doesn't exist, then it's impossible to decode. There have been too many errors. Make sense? And then so that's all the algorithm is. So the algorithm is find the polynomials using linear algebra. It's like linear algebra you learn in like 257 or 416 or whatever. It's literally just set up the matrix and solve the system of equations. And if there's no solution to this system, then return none. And if there is a solution, we'll test that solution. If that solution doesn't work, then we'll return none, and otherwise we've found our polynomial we want. Right? Just some linear algebra, and then do some checking at the end that we don't have too many errors. We found the right polynomial. And then so how fast is it? So doing linear algebra on n linear equations, it's going to take O of n cubed time, and that's just from doing like the row reduction, whatever stuff. And that takes n cubed time. Polynomial division, so computing f of m or f tilde of m will take another O of n cubed time. That's just because of polynomial. division, it's not super important why it takes that long, it just does. Computing C will take O and K squared time, and that's because so this polynomial F is of degree K minus 1. And then for each evaluation, so for each of the n evaluation points, you need to evaluate the polynomial F on that evaluation point, and that takes around K squared time because of all the exponentiation for each term. So it takes O(n) K squared time, which is less or equal to O(n) cubed time. Simple enough. And then just computing the differences, you just go character by character. That takes O(n) time, not too bad. And so overall, it takes O(n) cubed time. Simple enough? Idea makes sense of the algorithm? Cool. Any other questions? Oh, I forgot to find the quote. Hey, take that quote. Okay, thank you.